So welcome to the end of chapter 2. We will look at 2.4 today. So in chapter 2, we've been exploring data with tables and graphs. And in 2.1, we began organizing data into frequency distributions to summarize the data. And then we looked in 2.2 at the graphical version of that, a histogram, where you could much more easily see the sort of shape of the distribution, how the data was distributed. And then in my morning class today, we looked at graphs that enlighten and graphs that deceive, which basically introduced a half a dozen other new types of graphs and ways of presenting and organizing data, and looked at a couple of ways that graphs might be made that are actually not clear and even deceitful in how the observer views them. And then we finish off today introducing in 2.4 scatterplots, which is another kind of graph, correlation, and regression. And specifically, before we get into it today, I do want to point out that later in the semester, we are going to revisit correlation and regression, and we are going to do much more analysis and do calculations and do a lot of work that's much more rigorous toward the end of the semester. But the introduction they give in 2.4 is very superficial. It doesn't go very deep. It just tries to introduce the ideas of correlation and regression for data in scatterplots. So let's begin. Key concept: introduce the analysis of paired sample data. So I have to look at what that means to have paired sample data. Discuss correlation and the role of a graph called a scatterplot, and provide an introduction to the use of the linear correlation coefficient. That's something that is calculated. We won't need to calculate it in this chapter, but later we will use StatCrunch to calculate that for us. But it's a specific result of a calculation called the linear correlation coefficient. And then provide a very brief discussion of linear regression, what the ideas behind that, what that means, which involves the equation and graph of the straight line that best fits the sample paired data. All right, so that's a lot, and this section is a little bit more technical and much more specific than the stuff we did in the first 3 sections of the chapter. So let's get into it. Let's look at this key concept. So definitions. Now they're going to define these words. They've already been talking about correlation. What does that mean? A correlation exists between 2 variables when the values of one variable are somehow associated with the values of the other variable. Now, also notice they're talking about 2 variables here, and that's why they're saying paired data. So maybe there's some algebra in your history before this class to think about the difference between when you were just talking about an x variable value, like solving for x in an equation, and when in different ways in math, they would talk about x and y variables paired together, and you would make an ordered pair with the x value and then the y value. That's what they mean when they say paired data values. So when there's paired data values, that means we have 2 different sets of data. We have potentially 2 different variables or 2 different things being measured. So for example, previously I've been using the idea of investigating how tall students at DVC are. That's one variable value, the height, the unknown value of how tall a student is. That's one data value. Maybe I could call that X or call that H for height or something like that. Well, maybe I could also collect a different data value. Like maybe I could collect also how much a student weighs in pounds or ounces or something like that. Let's say pounds. So then I would have one set of data that showed me a bunch of different heights of students. And then I would have another different set of data that had a bunch of different lists of weights of students. So the idea of whether a correlation exists between those two variables is if there was some association between how tall someone is and how much they weigh. The simplest kind of correlation might be that when the values of one of the variables gets larger, you see a correlated or corresponding increase in the values of the other variable. Do we believe on average that tall people weigh more, as a simple example, and that short people weigh less? That doesn't mean every person who's a little taller than somebody else will weigh more than them, but is there simply a correlation between the two that in general, on average, if you're taller, you probably have an average weight that's higher? Something like that. Questions, comments, discussions about the idea of correlation existing between two variables? Okay, here's your chance to wrap your mind around the ideas more fully. Try if you can, and share it if you're willing. Try to think of an example of two variables representing something that would be measured, and whether you would consider there's a correlation between the two. And it may be that you're thinking of two things where you think there's no correlation, or maybe there's two things where you suspect there is a correlation. But just the idea that you could measure two things and imagine, are they related in some way? Do we think there's a correlation between the values of these two variables? See if you can imagine that and think one up. And if you're willing to share one, offer it up to the class, that would be great.
I have one. Well, I think I do have one. The temperature and time.
So you could just literally make a variable as to what time it is, maybe time of the day, measuring in hours or something like that. And then you could also make measurements of temperature. Now, I'm going to add an extra component because your example, it makes it even easier to do that, and I need to do that as well. When you have these two different things that are measured, when you have paired values, so in the earlier slide, it referred to the idea of paired sample data. When you have paired values, what we're going to look at is not just having a big list of height and a big list of weights, but you're going to go one step further and pair this person had this height and that weight. You're going to pair the two together. And that's going to make an ordered pair like the old X and Y's that you might have done in some nightmare algebra class from years past. And so I don't just have a bunch of heights and a bunch of weights, and I don't know which comes from which. To see if there's a correlation between the two, I need to know if when the height gets bigger, the weight does too. And to do that, I need to match those up. I need to have them paired together. So in the example just provided of time and temperature, I might measure the temperature and then pair with that what time I measured that temperature. So I will have a bunch of temperatures and I will have a bunch of times, but they're linked together because I know at what time each temperature was taken, as an example. So that's a great example. Thank you for offering that. That's a perfect example where we could think about, is there a correlation? For example, during certain times, is it hotter? Is there some relationship between the two? Maybe afternoon times it's hotter, evening times it's colder. Might be an obvious example, something like that. But also that's a perfect example of thinking how naturally, as you were collecting the data, you might pair the two together and we would form these ordered pairs. Great example. Anyone else want to offer up a possible example of two measurements that would be collected and how we can imagine or a lack of or an existence of a correlation between the two? All right, let me give you one more example and I'll just modify the one that I did before. I could measure people's heights, students at DVCs. And then as I got their height, I could also have them sit down and take an IQ test. Because maybe I was suspicious, and I'm not going to say I'm biased here, but maybe I'm suspicious that short people are smarter. Now, I'm expecting that I would find out actually there's no correlation between height and IQ. and that would be something to investigate. But I could consider it, and then I could imagine trying to think about, is there a correlation between height and IQ score? And I could collect those data in paired values, and then we'd need to use some statistics to investigate that, as we will see shortly. Questions, comments, discussions about correlation? All right, so then the next step in a possible correlation is if there is a linear correlation. A linear correlation exists between two variables when there is a correlation and the plotted points of the paired data result in a pattern that can be approximated by a straight line. So of course, that's a graphical description, and this is one of two. So hopefully our next slide may show us a graph to think about. But the basic idea with what a linear correlation would mean, to make it simple, is that imagine that a correlation causes one variable to rise, then the other one variable rises, or one variable to decrease, then the other one decreases. Or it could be that when one rises, the other one decreases, or that when one decreases, the other one rises, that there's an inverse correlation. But in either case, they're linear if basically proportions stay consistent. What does that mean mathematically? If I double one, does that double the other? If I decrease one by half, does the other one get decreased by half? If they sort of inflate and deflate in a same proportional way, that's a linear correlation. Or maybe I double one and that halves the other. Or I cut one in half and that doubles the other. Then that's an inverse but still linear correlation. So that's the concept behind it. It's much easier to see with a graph. Let's see what we get next. No graph yet. So they're going to define what the graph is that allows us to then investigate these points of paired data. When you graph like X and Y values of the pairs of data values that you've collected onto an X-axis and a Y-axis, or maybe a height axis and a weight axis, as an example, then that creates what's called a scatter plot. A scatter plot is a plot of paired X and Y quantitative data. Quantitative means numerical, a horizontal X-axis and a vertical Y-axis. And the horizontal is used for the first variable and the vertical axis is used for the second variable. Which one is first and second? That's up to you, and you can change that when we're looking and making graphs. But you do want to think of X being first and Y being second, because that's the convention. X comes before Y in the alphabet, things like that. All right, so that's what it is. Thank you for a picture. All right, so this is what an example of a scatter plot would look like. And it also means that what we're looking at is points where each point on the graph represents one of our paired data values sets. Like in this case, the two things they measured was waist circumference, distance or length around your waist in centimeters, and arm circumference, size around your arm measured, distance around your arm measured in centimeters, maybe like with a tape measure. And so you could sort of imagine, if I measure arm circumference and waist circumference, is there a correlation? Meaning that perhaps if someone has a bigger waist, does that usually mean they also have a bigger arm circumference, or vice versa? And so when you see all the data values, each data spot here is a person and their arm and waist circumference measurements. And so if you look at this, you can think of these as people. And what you can see in general is that as the waist measurement for people goes up, it looks like also that their arm measurements on average rise as well. That you don't really see a bunch of people with a very large waist and small arm, or vice versa, a very small arm and a large waist. Actually, that's the first one I said. Over here would be large waist, small arm, and over here would be small waist, large arm. But you see people kind of running along the middle, where they go from both are small to both are big, and it kind of gradually progresses. Now, this is still kind of a cloud, but it kind of follows this uphill pattern in a certain direction, and that means it's somewhat linear. So in this case, it says the distinct pattern of the plotted points suggests there is a correlation between waist circumferences and arm circumferences. So that's a lot to take in, and this is our first picture. Questions, comments, discussions about what we're seeing here or what the meaning is?
Professor, for example, correlation, linear correlation, is that called?
Linear correlation, if it looks like kind of like it's going in the direction of a line, yes.
Is it like you can use that, for example, in economics when you are measuring like the with like the price, when the prices go up and the demand goes down?
Yes, and that kind of a graph that you'll see in economics is perfect examples of using what they believe with years and years of evidence to have a strong correlation. Now, in the simplest forms of those graphs, they will represent that with a line, but often it's not necessarily linear. Like it might be that as the price goes down, then the demand goes up very, very quickly, and that it kind of curves and has more of a, and then they'll call that the demand curve. A curve doesn't mean it can't be a line. A line is an example of a curve, but it also opens up to the idea that there may actually be curvature. And that means that it's sort of bent or, not in a straight line. And so they'll call that the demand curve, and then they'll compare that to the supply curve and things like that. But in both cases, they're saying that the demand and the price, there's a strong correlation between those two. And in that case, it's an inverse correlation. The higher price, the lower the demand, and the lower the price, the higher the demand. That's an inverse correlation. Whereas the supply, there's a positive correlation, because the higher the price of the object, the more people want to supply because they can make more money for it. Oh, lost my share there. Does that make sense?
Yes. Yeah. Thank you.
So you are giving a very good example in economics where these kind of things are observed, and they often use a linear. They usually represent those correlations with a line to keep it simple, and because sometimes that relationship is fairly easily linear. Great example. Let's go ahead and move forward, because one of the things they're going to do in this section is look at different scatter plots and have us begin to just ask ourselves the question and judge for ourselves, do we believe we observe a linear correlation? So here's another slide, and before they did waist and arm measurements, but now they're doing weight and pulse rate, meaning how many times your heart beats per minute. And these are actual data values, and I believe it's from data sets that are included in the textbook appendix and can be searched online. But nonetheless, these are data values they've made a scatter point for. So they're suggesting from this picture that there doesn't really seem to be a correlation. There's no correlation here. The plotted points do not show a distinct pattern, so it appears there is no correlation between weights and pulse rates. Now, pulse rates, resting heart rate, is often something that is a consideration of good health. For example, athletes usually in general often have lower resting pulse rates. And as people are not very athletic or become more of a couch potato, it might be sometimes of concern if their resting pulse rate gets higher. That can lead to high blood pressure, things like that. So people who are also worried about weight or obesity or things like that not being good for health, they might think that naturally there's a correlation between weight and pulse rate, and that maybe people who are unhealthy and have a very heavy weight or overly obese might also therefore have a high pulse rate and be, having problems in that area. But actually this data doesn't show that at all. And that it's perfectly quite possible to be higher on the weight side and have lower pulse rates. Now, I do see kind of a gap in this corner, but I don't see a clear pattern that you need to have a lower weight to have a lower pulse rate. That does not seem clear at all, and there is no real clear correlation here. So this is an example of a scatter plot where we could look at it and make an assessment about correlation. but I'm also trying to describe the idea and the purpose of someone wanting to look at data and investigating the idea about a correlation between two variables. Questions, comments, discussion about this slide in particular and this example? All right, let's keep moving. So once you are in a position to collect data, make these ordered pairs, maybe even look at a graph of the results, look for patterns, then we are also in a position to use some fancier math and actually measure an idea of a correlation. In particular, we're going to come up with this variable R called the linear correlation coefficient. Again, it's just a result of a calculation, and we don't need to worry about how the calculation is done. You never really will need to, because even when we're doing it ourselves, we're going to use a calculator to do it anyway. But what does it refer to? A linear correlation coefficient is denoted by R, and it measures the strength of a linear association between two variables. It basically measures how strongly the paired data values adhere to a straight line. The strength of a linear association. Excuse me. So what is going on and how do we use this R? The computed value of the linear correlation coefficient R is always between a -1 and a +1. So you'll never have an R value of 2 or 3 or -7. It'll always be a small little number. It's usually given as a decimal because it's less than 1. You might even think of it as a percentage. But something like 0.5 or -0.3, something between -1 and 1. That's the kind of number R will always be. Because of the way the calculation is done, you can't get anything outside of those values. So then when you're looking at that value, if the R value is close to -1 or 1, then there appears to be a linear correlation. So being closer to the 1 values increases the strength of the linear correlation. Then moving away from those and getting closer to 0, which is right in between -1 and 1, as you move away from the extremes of 1 and -1 and move to the middle where the 0 is, that's when you're losing your correlation. And that means there is not appear to be a linear correlation. Think of the 0 as no linear correlation and 1 meaning like 100%, yes, there's a linear correlation. And for those who are a little comfortable with the line math from algebra, you may recall there's this thing called the slope of a line. And when the line goes uphill from left to right, it's a positive slope. And when line goes downhill from left to right, it's a negative slope. That's why you would get a negative or a positive R correlation coefficient. If you have an R value that's close to 1, not only does that mean there appears to be a correlation, but it's a positive correlation, meaning when you raise the value of one of the variables, you're tending to cause the value of the other variable to raise as well. They both go up together or both go down together. When you have a -1 or close to a -1 for your R value, that means, yes, there's a linear correlation, but it's sort of inverse, meaning you raise the value of one, it causes the value of the other to decrease. It's downhill. The line that it looks like goes downhill from left to right. All right, let's let some pictures help us with this if they give us one. Okay, so now we have another example. And this time they gave us data values listed out here. They gave us 5 paired data values, one having to do with shoe print length and the other having to do with the height. So I think these are paired by a person, how big their shoe print length is and how big their height is. And they can see here, they've measured the shoe print. That's the first variable along the horizontal axis or the x-axis. And then they've measured the second variable along the vertical axis. That was the second variable was height. And they got this little scatter plot pattern in the graph. So the natural question would be is, do we think this suggests there's a linear correlation between the two? We looked at some examples before, one with a linear pattern, one without one. This is kind of in the middle, kind of like split apart. I don't know. Let's see what they say. Well, they say with these data values, we could toss them into a calculator. And the one they used this time is called StatDisk. We are going to continue to hopefully use StatCrunch, and I will continue to emphasize that. But the book doesn't know which calculator device you might use, so it kind of bounces around and tries different things at different times. But what they did was when they put those 5 data values in here, they got a linear correlation coefficient R. And you can see it in the box there. The top line says linear correlation coefficient R was 0.5912691. And what they are saying here is this isn't very clear whether there's a linear correlation. And the graph didn't look very clear either. The numbers kind of between 0 and 1, sort of in the middle. Sometimes you don't get very good clarity from the data. Now, also, this is a very small data set. They only have 5 values of data. If we had more of those dots on the graph, we might be able to get a better idea of whether we think there's a linear correlation. There seem to be so few here. So let me just pause here and just see if there are any questions before we move on to a definition of a p-value. Any questions about this? Okay, so now we have p-value. If there really is no linear correlation between 2 variables, the p-value is the probability of getting paired sample data with a linear correlation coefficient R that is least as extreme as the one obtained from the paired sample data. I would believe that that statement makes sense to absolutely no one. P-value is a fairly complex concept, and we are going to be exploring it and using it throughout the semester. And my honest opinion is this is a very terrible first introduction to the idea of a p-value. So I'm just stating that because if you read that and you're like, what the hell are they talking about? I think that's normal, and I would be shocked if anybody read this and it made sense to them when they first read it. So I'm just illustrating that fact and also pointing out that even though this is very confusing, one, it's very important because it's one of the key concepts in statistics. But 2, because it's important, we're going to be looking at it a lot and you're going to have a lot of time to think about it and it's going to be used again and again. And this is just an initial introduction. So if I were to try to give an example, if we go back to this previous statement here, this linear correlation coefficient R was close to 60%, 0.59, I'll say, something like that. So that is not a very strong indication that there is a linear correlation in the data. But again, it's not 0. It doesn't mean there isn't any at all. So that's why it says it's not very clear. So right below the red box, they actually give a calculated p-value for this data. And it's 0.29369. So that's a probability value. Now, one of the reasons I think discussing probability at this point is too early and not done very well here is that chapter 4 is all about probability. The entirety of chapter 4 is about probability. So it'll make much more sense for us to discuss probabilities in chapter 4 after we've done chapter 4 and certainly while doing chapter 4. So to do that in chapter 2 at the very end is not the best educational approach. So I'm just trying to make that extra clear because I want to tap down natural anxiety for them discussing something at this point, which doesn't make sense and is quite frankly a little inappropriate. So having said that, I will still try to say what it means because they gave us this definition. It's the probability of getting paired sample data with a linear coefficient that is at least as extreme as the one obtained from the paired sample data. Oh, what does that mean? So what that means in this example is that from our 5 data values, we got a linear correlation coefficient of 0.59 approximately. And the p-value is 0.39. So I'm going to call that 30% and the 0.59 60%. What that means is that there's a 30% chance that you could get that 60% of an R coefficient by random chance, by randomly picking 5 points, even if there was no linear correlation at all. That you just by chance happen to pick points that seem to have a possibility of a linear correlation. So that means if you collected the data and you saw this R coefficient of 60%, the p-value tells you, well, 30% of the time you'll get that result, even if there's no correlation at all. So how good is that at telling us there's a correlation? Not very good. You could easily just get that by chance. Anything more detailed than that and probably just make things worse if I tried to explain it better. So having said that, does anybody want to try to formulate a question about p-value? They just are, here's the slide where they're interpreting it as I just tried to do. Questions, comments, or discussions? Now, to make things worse, I don't know if they do this in the book. I don't think it's in the slides. There's the correlation coefficient for the population uses a symbol called rho, which is like a Greek R, but it looks like a P. So that gets confused with p-value as well.
I have a question.
Yes, go ahead.
How would you know whether the p-value is high or low?
Well, it'll be calculated by the calculator, and a probability will always be a probability between 0 and 100. And again, we'll study that more in chapter 4. But if I say there's a 0 chance of that happening, that means it's not going to happen. And if I say there's a 100% chance that's going to happen, well, that means that's a 1. 100% as a number converts to a 1. And so probability values will always be a decimal between 0 and 1, where 1 is an absolute certainty and 0 means there's just no chance. And so you don't have to calculate that yourself. You just want to be able to interpret it when they give one to you, or when your calculator gives one to you. Does that make sense?
Yeah.
So when they say p-value of 0.029, you're basically saying, okay, that basically means there was a 30% chance of what happened here would happen just randomly. Great question. Other questions or follow-ups in any way? Comments?
It's saying that there's a 30% chance of R being 0.6% chance?
No, the number we have for R is what R is, but it's the R value of our sample. And remember, in statistics, the big picture is that you are specifically looking at exact values of your sample to try to then extrapolate and draw conclusions about a larger population that you picked your sample from.
Oh, I see. I see. Thank you.
And so our sample had an exact R value of 60%. The probability is the chance or the likelihood that you could get that R value from a random sample of 5, even in light of the fact that there's just no linear correlation at all.
I see. That makes sense. Thank you very much.
Because you just randomly grab 5. You might get some that kind of line up in a row just by random chance. Well, in this case, they're saying to get this level of lineup, that'll happen 30% of the time when there is no actual lineup in the population. There is no linear correlation. You still might see a little lining up of data if you just randomly pick 5 just because of random chance. Is that more clear?
Yes, that fixed my perception. Thank you very much.
Very hard concept, and if you're not up to the energy of following through with this at this point, don't stress about it. We'll have a whole chapter to discuss what probability is, and then later we'll have I think a section or two of chapter, maybe even 11, maybe our last chapter, where we revisit linear correlation. It might be 10 though, 10 or 11, something like that. All right. So here's their attempt to make the sentence that I was also just trying to make. Let's see if it matches. Interpreting the p-value from the example where n is 5, because the likelihood of getting that 60% R value or more extreme is so high, 30% chance is a high likelihood, meaning it could happen fairly regularly, we conclude there's not sufficient evidence that there is a linear correlation between the shoe print lengths and heights. All right, so honestly, everything they're doing here, they shouldn't be doing here, because we go into this in much greater detail later. They kind of think just putting it in your mind early lays the seeds and the groundwork for later. My experience is in it, just putting it in your mind before we're ready to talk about it is just confusing. But it is here, and I'm not going to try to take it out. It's in the book. So we'll just do our best with it, and I'll just try to help people tap down any anxiety they may feel by just pointing out that they're kind of talking about stuff that we're not really sophisticated in our statistics yet to discuss in any detail. So then they go a little further and they give you their first introduction to what kind of a p-value is often considered acceptable. Only a small p-value, such as about 5%, suggests the sample results are not likely to occur by chance when there's no linear correlation. So imagine the idea that if you looked at your data and it all seemed to line up really nicely, then you would think, wow, what's the chance that it would line up that nicely if really in the overall population there was no linear correlation? Well, that's what the p-value tells you. And if the p-value is very low, that suggests, well, that's really not that likely. And then that supports the idea that the reason you're seeing lineup in your sample is because there is a lineup in the population. And this logic will be at the heart of all statistics, and we will discuss it in super great detail when we move into something called hypothesis testing in chapter 8. So even this key nugget of a concept they're introducing to you early is very important, but still also being introduced very early. But in general, a low p-value allows you to draw conclusions that what you saw in your sample is a good reflection of what you expect to see in the population. Questions, comments, discussions about that? All right, so let's look at one more example, and then maybe we'll try to hop over to a homework and see, like, I want to definitely make sure I show everybody how to make a scatter plot using StatCrunch, so that these graphs that they're showing you, if they give you data, then you can make one of these graphs with a data set that they give you. So here's an example, and this is actually the same comparative we just were doing, but they've moved from having only 5 pieces of data to many more. So the 5 data values they showed us before, they're also included here, but there's a lot more included. So they're still comparing shoe print length to height. And in this bigger data set, now they have 40 pieces of data, and they're also showing the number n. N is the letter we typically use to represent how many pieces of data were in the sample. So previously we had a sample size of 5, and now we have a sample size of the same data, but there's 40 pieces of data. Now it says here the Pearson correlation of shoe print length and height equals 0.813, and a p-value is 0.000. So let's see if they give us a slide to interpret this. Yeah. The scatter plot shows a distinct pattern. The value of the linear correlation coefficient was now over 80%, and the p-value dropped down to nothing, at least to 3 decimal places. And because now it's saying basically there's no chance that you could have taken 40 data values and gotten 80% correlation coefficient, that's just never going to happen by random chance, then we have sufficient evidence to conclude there's a linear correlation between the shoe print lengths and the heights. Questions, comments, discussion? Yeah, it's overwhelming. You know, when I looked in the homework, I think the homework on this last section, there's only like 5 problems out of 40 something. Like 10% of the problems are on section 4. So this is probably a good reason why. So they're going to say, all right, well, we're going to introduce this idea, and then later we will actually come up with these equations, but they're going to introduce the idea of regression now, and then in a later chapter, we will actually work with it. Given a collection of paired sample data, the regression line, or sometimes referred to as the line of best fit, or least squares line, is the straight line that best, in quotes, fits the scatter plot of the data. In other words, if you're looking at a scatter plot, you're saying it's kind of like a line. Well, where would you put a line that you think would best represent what you're seeing in the scatter plot? Well, there's a formula that we'll work with later to actually produce that, but again, it'll be used, the calculator will do it for us. And then once you have that line, then you can say, well, this line is the best attempt to show the linear correlation between these, and that's called the regression line or the regression equation or the line of best fit, least squares line, etc. So they introduced this idea that when we're talking about a linear correlation, at some point we're actually going to come up with an equation for that line of the linear correlation that we're talking about. So here's the example of the data set we were just looking at, and they've added to the scatter plot graph the line of best fit, the regression line. And the calculator did that. And so if you are going to imagine these data values and these 2 variables having a linear correlation, then this is the line that would best try to describe that. Now, plenty of the data values, you know, vary from this line quite a bit, but notice they don't vary anywhere down in this bottom corner at all, and they don't vary up in that top left corner at all. And so they're kind of hovering around the line, and that's the best indication of what's going on. Apparently, one more slide to finish this up. So they're showing that that's another thing the calculator could give you if you entered these paired data values into a calculator. Again, this is what it looked like in StatCrunch. I'm sorry, in StatDisk, not StatCrunch. StatCrunch is much better. You could see that they give you the correlation coefficient, that R value. There's this P value, the likelihood that you could get that big an R value with this many data values by chance if there was no correlation. And the bigger R is, and the more data you have, the lower the P value will be. And then actually it'll give you the equation. It'll say, all right, here's the regression results. The line that best fit would be one where the intercept value, which is B sub 0, is this number, and the slope, which is the number in front of the X, is this number. And they describe that here, and they show you how you could sort of interpret that. And if you were then going to observe this and think this is the line that best fits with how the data is correlated to each other, you could actually use that equation where you plug in a shoe value and you do the calculation on the right to then predict a likely height value. And that's why these things are done. Because if one somehow is related to the result of the other, then you can try to use one to predict the result of the other with at least better accuracy than perhaps just a random guess or something like that. So it did not finish comfortably, but it did finish. That is the end of our slideshow. I will point out that the much more important parts of this are the scatter plot and just the idea of a linear correlation at the beginning, and that's the introductory concepts that we want to really think about and try to maybe make and judge some scatter plots, which I'll demonstrate in a second. But let me, while we're here with the slides, ask if there's any questions about any part of the slideshow, anything I should explain better or elaborate on, if there's a desire for me to do so.
Yeah, I have a question on finding the critical value of R. It was discussed in the book, but I'm not seeing it on the slides here.
Yeah, they show it in that it's one of the things that the calculator might do. So let me show you that. So you can see right below the correlation coefficient is the critical value. basically the critical value is the minimum size number you'd need to hit to conclude there was a linear correlation. And that will be based on how many data values you took. And I think there's a problem in the homework where they ask you to do that. But what they do is they give you a little chart, and it shows you with this many data values, you need this R value, and it gives you a little list for you to pick the critical value from.
Yeah, that's the one I'm stuck on. It's the last question on the homework.
All right, maybe we'll use that as an example today too. We still have about 11 minutes. So how about if we hop over there now? I have one where I want to show people how to make a scatter plot. And then if there's time, I'll also show how to use that chart. And if I run out of time, I'll stop the recording, but I'll probably still hang around and help you and answer questions afterwards. Any last minute questions before we leave the slides? All right. Okay, so I'm going to hop over to, I'll leave the recording going, and I'm going to hop over to the homework set. And the one I wanted to look at, just because I saw we could do a scatter plot, I think is 47, maybe. Yeah. All right, so in number 47 from our homework, which is due Sunday by midnight, this is 47 out of 49. So there aren't many problems really on 2.4. I think it's like 45 through 49, like the last 5 problems are the only ones from 2.4. But looking at this one, they give us a set of paired data between tar and carbon monoxide is CO. Yeah, carbon monoxide. Anyway, they give us these paired values, and they want us to say, what does the scatter plot look like? And you can see there's some choices here. So that means we're supposed to make the scatter plot so we know which one of these makes sense. I mean, you could, just so that you understand, you can blow up these graphs, and then you could look at the actual values and see which one has pairs of values that match the table. You don't need to make the graph yourself. You could just check the table values against the shown graphs, but that's harder, and it's good for you to be able to make a graph. So let's see how to do that. So as we've seen before, when we're given data, there should be a little box up here, and then we can just open in StatCrunch. And what you can see in this case is there's 2 columns of data, and that we have paired values in each row. So a scatter plot is a kind of a graph. So I would go to the Graph tab. Here's the histogram that we did in 2.2. In 2.3 is dot plot, as an example. That's there. And here is scatter plot. So I went to the Graph tab and I select Scatterplot. So now I need to tell it which column is my horizontal x-axis, which is the tar. And so that's the x variable. So I have to pick, and I pick tar to match what they did here. That's going to be my first variable. And then for y, I pick the CO, carbon monoxide. So let's try that, see what we get. So now we have a scatter plot, and we can try to match it up against which of these seem to match. Like I see this little U-shaped pattern with these 4, and that's pretty much in the C. And in fact, the U kind of goes to the side in the D. So I'm going to point out to you that the difference between C and D is that in D, they flipped the points. They flipped the axes, because they want to see if when you tossed it in a calculator, you entered the tar for the y and the CO for the x instead of vice versa. And if you made that mistake, they wanted to have a graph for you to pick because you made that mistake and get it wrong. So if you don't put the axes in the right order, there may be a wrong choice here to show you that result. But we did put them in the right order, and that would suggest that that is C instead of D. Questions, comments, discussions about how we made a scatter plot using StatCrunch with given data? All right, now let's see here. Let me go to the edit, and that'll go back to those options where I selected these. So I think down here they also have display points and they have lines. I thought this one we can add the line somewhere. Maybe I'm forgetting how to do it. Lines might connect the points with lines. I wanted to see if I could put my line of best fit in here, and I thought you could. But it might be I need to do that in a different place. I'll have to figure that out. They're not asking for that, but I know you can do that somewhere in there, and it would be nice if I'd remember, but I don't. Anyway, so that's how you make a scatter plot. All right, so and then you wanted to look at the last one you said was the one that had the question about the critical value. Let's see here. Yeah.
Oh, I think it was actually 48. Yeah, that one.
48. All right, let's go to the question. Okay, so in 48, it says for a data set of brain volumes and IQ scores of 5 males. So they knew some people's IQ scores, and then at some point, they were also able to figure out their brain volume. They're telling us that they got a linear correlation coefficient of, looks like over 95%. That seems pretty strong. Use the table available to find the critical value of R based on a comparison of the linear correlation coefficient and the critical values. What do you conclude about a linear correlation? And then there's this table here. Okay, so here's what they give us. So the question is, how would we use this to find this critical value? Before we saw that critical value did seem to be provided when it was done on a calculator, but here they're not telling us what the data values were. They're just telling us that the result was an R value given, and they want us to come up with the critical value. Well, to use this table, what you need to do is look up the number of pairs of data you had, and then you get a critical value here. So can we, from the description of the problem, figure out how many pairs of data there were in the data set?
Yeah, I guess it would be 5 for
Exactly.
5 males.
Perfect, because the two things being considered was brain volume and IQ score, and they did that for 5 people. So that means the number of pairs of data N would be 5. Remember in our sample, we saw one where N was 5 and another where N was 40. Well, then what it says is to conclude that there's a linear correlation when you only have 5 data points. Because you have so few, and it could happen by chance more easily, you need to have a pretty high R value to draw that conclusion. The critical value you need to have is 0.878. Now, in addition to that, remember, R values could be positive or negative. And if you get up near a positive 1, you have linear correlation. But if you get down near a negative 1, you also have linear correlation. So even though they're only showing you a positive value here, the critical values for R will be positive and negative. So I would put that negative that number is 1. And then I would separate these by a comma because it says use a comma as needed. And then the positive of that value is the other critical value, just by reading it off of that table. Are you satisfied by that?
Yeah.
Okay. Now, then we're supposed to make a decision about that, just to finish up the problem for a little closure with our last couple minutes. So then we would compare the R value of the data to how big it needs to be to conclude there's a linear correlation. And if the R value is at that level or more extreme, we conclude there is a linear correlation. And if not, if it's closer to 0 than those values, then we can't conclude there's a linear correlation. So what do you think happens in this case? How does that, the actual R value we got, compare to the critical values here?
Well, it's greater than the maximum, so greater than 0.878, and it's close to 1. So it'd be a positive correlation.
All right, so let's see what choices it gives us. Since the correlation coefficient R is, and it sounds like from what you said, in the right tail above the positive critical values, what happened in this case, right?
Yeah.
And because of that, we conclude that there is or is not sufficient evidence for a correlation.
That there is.
Well done. All right, So we looked at, I think, 2 of the 5 problems on this section on your homework. There aren't too many of them, luckily. But it is a tough section conceptually. The big thing I want to make sure you get out of here is that you know how to take paired sets of data and dump them into a scatter plot when needed. And then hopefully you begin to think about this idea of a correlation, a linear correlation and its coefficient and those concepts. But you don't have to go too deep there. There aren't many problems on the homework. And we're going to go into those details much later, probability details in chapter 4 and linear correlation details in chapter 10 or 11, one of those 2. So any questions about anything to finish up today before we end the class session? I think I'll just stop the recording now. All right, well, we're about out of time at the end of class. So great job. Keep up the hard work. Come to office hours if you need to talk to me. We're going to begin looking into chapter 3 on Thursday, but I know people will probably still be working on chapter 2. Hopefully now you've had an introduction. I hope to post the videos for 2.3 and 2.4 sometime tonight. It always takes some hours to process the videos. Then I edit them a little bit, and then it takes an hour or 2 to load them up onto YouTube. And then I have to post the links. So probably won't be able to finish before sometime tonight, but they will be there. And we're all done, but I will hang out now and answer any questions anyone has. If you want to stay after and ask anything, then please feel free. I'm here to help.
Thank you.
Thank you.
Thank you.
Have a good one.
Oh, hey,
Hey, Caleb.
sure. Hi.
How are you, sir? Just you and me.
Good,
So
man.
feel
Yep.
free and comfortable to ask anything you want.
Okay. So I kind of wanted to go over I think the last question of the homework. I mean, I got it. I finished it already.
Okay, great. Good
But
for you.
I just wanted to go over it again.
Okay, so
I really don't
maybe
wanna-
I'll just go back to sharing what we were just looking at, and then we can look at it together. Does that make sense?
Yeah.
Let's do that. Share, and then I'll just go to the last one. This one?
Yes.
So they're still talking about brain volumes, IQ scores. This time they have 6 males, and now they're talking about the p-value instead of about the R linear correlation coefficient. And so they're not showing us the data. They're just telling us the p-value that the calculator gave them, and it was 0.833.
Mhm.
So again, that means 83%.
80%. Okay.
Just think of it, for now, we'll talk about probability way more, all of chapter 4. But right now it means there was an 83% chance that something happened. That's the probability that they're talking about.
Okay. And then for my homework, it gives me a 33% chance, 33.8. And then, so you said 80% was high. And then here it
That was
says
for
30.
R, not for P.
Oh, for R. Okay.
So when we were talking about P, there was even a slide that specifically said, when we talked about P, it was 30%, and they said that was too high
Mm-hmm.
in the slide.
Yeah. Okay.
And they said that you want the p-value to be low in order to draw a conclusion about linear correlation. And they said usually below 5%.
Okay.
That's what they said in the slide. And that's the rule of thumb.
Okay.
The p-value indicates the probability of a linear correlation coefficient as big as this or even bigger, that happened just by chance, even though there was no linear correlation.
Mm-hmm.
So if you want to conclude that there is a linear correlation, you can't have a high chance that the results you got would have happened just by chance, because that's not very convincing.
Yeah.
Instead, you want to say, well, look, the chance that we got this randomly with no linear correlation is so low that really there must be a linear correlation. That's the logic.
All
So
right.
they're trying to basically squeeze that logic out of you in this sentence. The p-value indicates the probability of a linear correlation at least as high as extreme is, and they're asking for a percentage.
Mhm.
And so they're wanting the p-value converted to a percentage.
Percentage.
So I would just put 83.3%. When you have a decimal, to make it into a percentage, you move the decimal 2 places to the right. Are you okay with that?
Yes. Yeah.
So that means the p-value indicates the probability of a linear correlation at that high is 83%, which is high. And I think they're going to want you to say it's high if it's anything over 5%,
5%. Okay.
because in the slide they said that's really what we want to be low enough. And when it's anything above 5%, then we say there's not sufficient evidence to be convinced there's a linear correlation, because this is the chance that you just got that randomly.
Mhm.
And if it just happened randomly, then there isn't one.
Okay, that makes
Think
sense.
about that description.
Yeah, that makes a lot more sense.
There's a lot of logic in there, and rest assured, we're going to be focusing on this logic multiple times. It's going to be the key to how we do statistics, basically beginning in chapter 8, 9, 10, and 11. And probability we'll talk about for all of chapter 4, just to be in a position to do those arguments later. We'll talk a lot about probability, but they're already trying to have you wrap your mind around the idea.